And so this morning, let's focus on this internal energy change. And one way to prevent work from being done by the system or on the system is to put it in a fixed volume. And we do this, it's part of a calorimetry experiment that we have available here in our PChem lab. We have a couple of these. And we will actually combust a sample inside this stainless steel chamber in pure oxygen. So we'll stuff, 15 or 20 atmospheres of oxygen inside this container and have a little wire and a little ignition circuit. You punch the button and the wire explodes and burns because it's in pure oxygen, and that sets your sample on fire, and your sample burns completely, we hope. I mean, that's the goal, is to completely burn your sample in excess oxygen. And to not have any volume change or any leakage around the threads. And that's the leakage is the problem. Sometimes these little things leak. But what have you got in that little steel container? I mean, it's a bomb, right? Yeah. We don't want it actually breaking the container, but it is a bomb. And so this is called bomb calorimetry. And so you put all the sample in there and you stuff in a ton of oxygen, excess oxygen, and then you light it up. And it's really anticlimactic, which is a good thing. We don't want it blowing up the instrument or injuring the students. You punch this button, the light comes on, and you're like, great, what happened? But then you see the thermometer, and it goes, starts rising. So all this combustion generates a lot of heat. And if we force the volume to stay constant, we haven't done any work. And so the heat released by that reaction is measured by the change in temperature of our calorimeter, and we've restricted work, so W is 0, and so we can look at the change in internal energy by looking at the heat generated. And so we can get to know something about a substance by burning it in pure oxygen, and we can get the combustion enthalpy, and we can get the change in internal energy. And so this is calorimetry, not colorimetry. So the change of one word. Last semester we did colorimetry, the RGB values, the XYZ, tristimulus values. That was colorimetry. And if you search for colorimetry, you'll probably have Google correct it for you, and it'll search calorimetry. This is way more common than determining the color of a substance. But this is something that I've run into every time I'm trying to find something on colorimetry. And Google will switch it and say, "Did you mean calorimetry?" No, I know how to spell. One thing, too, is we talked about measuring the temperature change of the calorimeter. And so all of these things have to be calibrated. And so we'll calibrate it with a known substance, like benzoic acid. So we'll burn a known substance, weigh it out, so we know how many moles we put in there. And we should know how many joules are generated. And then we see a certain temperature rise. And so we know how many joules we delivered. We know what the degrees were. So now we have the calorimeter constant. And then we can burn an unknown and see. A lot of times students like to do food, and so you're not really going to be able to get the number of moles of starch, but you'll have grams. And so you can see how much energy is generated per gram of carbohydrate. Or if you have something that's high in protein, you could get sort of some ratio of protein to carbohydrate. And if you know the carbohydrate number, you can figure out how many grams of heat are generated by burning protein. And then you could have something that's high in fat. And so then you can see how many grams from fat. So you can get nutritional values from this. And you can see that it lines up with what's on the label. So it's pretty cool. So a lot of students will do food in these, yes.
How would caffeine interact with this?
It would just burn like any other substance. So that would be if your body just naturally, instead of just dealing with the neurotransmitter effects of caffeine, if it just burned it as it burned any other hydrocarbon food or carbohydrate food, you would get the calories from that. So this would tell you how many calories you could get from caffeine. Yeah. In a combustion situation where your body sort of applies oxygen to it and turns it into CO2. Yeah. And so we could we could calibrate this calorimeter using voltage and amps and time. So we could put an electric heater in there. And some years we've done that, other years we've just used benzoic acid. Benzoic acid is, I think, more representative because we're burning it, and so we'll use benzoic acid this year. But if you put in a resistor and you run a certain voltage and a certain amps through that for a certain amount of time, then I just wanted to make sure you knew how to calculate the amount of joules. So an amp volt second. So current times volts times time will give you the number of joules. Okay. And so these are just some example problems I have in the notes for you to look at. It'll help you understand some of the stuff about your household electronics, right? So if we put in 3.6 times 10 to the fourth joules, or 36 kilojoules, what's the calorimeter constant if this caused a 3.6 degree rise in temperature? Well, it's the amount of joules in divided by the amount of temperature change. And so it would be 10 to the fourth joules per degree. So it takes, and these calorimeters, you know, they're bulky. They have 400 grams of water. They've got a glass dewar. They've got a steel container. You're changing the temperature of all of that. And so it takes quite a few joules to change at a particular degree. And so this is saying it's got to take 10,000 joules to raise it 1 degree. So we need a really sensitive thermometer. Well, you have these resistance thermometers. And so if you have a calibrated length of platinum in your thermometer, and you know its resistance because it's an intrinsic value of metals. You've got a very pure electrode, this platinum electrode, and you're measuring its resistance. That resistance is a function of temperature. So you have a really accurate thermometer by using the resistance of a length of wire of platinum. And so that's buried in this little steel probe that we stick down in there. And this platinum resistance thermometer can give us temperature out to the 4th and 5th decimal place. So you really see very small changes in degrees. And so you'll be able to see it drifting just with room temperature. And then it looks kind of noisy down in the 3rd decimal place, and then you fire the bomb and it starts changing. You might get a 2 degree rise in temperature, which you think 2 degrees, that's not very good. But the noise level is so low that you can definitely measure, you know, probably 3 or 4 significant figures with a 2 degree temperature rise. Just for household calculations, how many amps does a 1200 watt hairdryer pull? Okay, so a watt is a joule per second, and that's an amp times a volt. So we can figure out, if we divide by volts, 120 volts in the wall, that's 10 amps. So that is pulling a lot of current. That's why you don't drop that in the bathtub with you, because it's current kills. Okay, it's not voltage. You can have, like I said, 10,000 volts of static electricity on you, and it just stings as it leaves the body. Okay, it's the current that goes through your body that can screw up your nervous system. Okay, let's talk about heat capacity. We've been talking about heat capacity for, several weeks, and looking at the change in internal energy with respect to temperature. So if you were to plot internal energy with respect to temperature, this would be the instantaneous slope. And we also have some funny looking derivative symbols here. This if you haven't had partial derivatives in your calculus class, which you might have, I don't know. These are partial derivatives. And so it's saying that the internal energy may be a function of temperature and of volume and of pressure and all these state variables. And what it's saying is it's saying let's just take the derivative of internal energy with respect to temperature, treating all the other variables as constants. So that's called the partial derivative. Okay. And so it's just saying, all right, just differentiate the internal energy with respect to temperature only and hold all the other variables constant. Now this is specifically saying hold the volume constant. When you see this volume down here in the bottom right corner, that's specifically saying at constant volume. So it's emphasizing that we're at constant volume. And so that's when we say CV, we're talking about the change in internal energy with respect to temperature. CP would be the change in energy with respect to temperature at constant pressure. And those are related. We'll see at the end of this set of slides how they're related. Now, when we deal with heat capacity, now not many people are very particular in how they speak about these things, but I'm pretty particular. So when I say heat capacity, I'm talking about molar values. And so we calculated for polyatomic gases, the heat capacity at constant volume per mole is going to be 25 joules per Kelvin per mole, roughly. Now, the experimental value for water, so liquid water, is 72 joules per Kelvin per mole. So it's quite a bit more heat capacity in liquid water. Why might that be? Remember our heat capacity for a gas, for water, we had translation, we had rotation, a negligible vibration, but there might be like 5% of that heat capacity coming from the vibrational motions of water, but almost nothing from that. And then water's almost 3 times higher than that. So what's new about water that's not present in liquid, in gaseous water? What's hydrogen bonding? So we've got some other kinds of vibrational associations that might be pretty low, right? There's also what we call acoustic modes. So these are vibrations of large groups of water attracted to other groups of water. And so those are elastic modes too, and you can store energy in that as well. So when you heat water up, you've got more motion in the molecules. Translation is reduced, but now that translation's turned into these acoustic modes. And there's billions of those, because you could have one water molecule banging around, you could have 2 working in concert, 3 working in concert. Think about how many pairs and triples and quadruples you could have, and then you've got X direction, Y direction, and Z direction for all of these. So there's just a lot more degrees of freedom in a liquid in terms of these different kinds of vibrations than there are in a gas. And so then that allows us to store more joules of energy per degree, because there's many more energy levels to fit that energy in. Now, notice the difference. Heat capacity is per mole. Specific, that word specific means mass. So when you see specific heat, you're talking about mass. And that's joules per gram of material. So for water, again, it's 4 joules per Kelvin per gram.
So, but it's the same idea, just moles versus grams.
Yes, it's the same idea. And so this is where that definition of a calorie came from. It's not on the slide, but 1 calorie is based on water. Let's just put the units. 1 calorie . So the specific heat for water is 1 calorie per degree Celsius per gram. And so that was the definition. How much energy does it take to raise water 1 calorie? Okay, 1 gram of water, 1 calorie. And so then that makes sense too, because there's 4 joules per calorie, and so it takes 4 joules to do the same thing. It's like 4.1. And so this is a really handy equation here. This change in internal energy is equal to that heat capacity times the change in temperature. So if we have a change in temperature, we can multiply it by the heat capacity and by the number of moles, or if it's specific heat, times the number of grams, and we can get the change in internal energy. And so since the work is 0 with constant volume, so CV in constant volume, you're not going to have expansion work. And so the only change in internal energy is the change in heat. So let's talk about enthalpy. If energy changes take place at constant pressure, but with variable volume, this is known as a change in enthalpy. So this is the parent equation for enthalpy and how it relates to the internal energy. And then we can look at the change. So if we take the derivative of this, the change in enthalpy, we take the derivative of internal energy and the derivative of PV, and using that product rule, we have P times dV plus V times dP. But then for expansion work only, we can plug this in for the internal energy. And we have a minus P delta V and a plus P delta V, so those have canceled. And so we have the delta H, the change in enthalpy is equal to the heat, plus V times the change in pressure. But notice up here we're at constant pressure, so dP is equal to 0. And so we end up with this relationship. The enthalpy is just the heat of reaction. So at constant pressure with expansion work. So if we find the heat of reaction, then we can get the enthalpy directly. And so that's why we call this enthalpy change the heat of reaction, because whatever happens in that reaction at constant pressure is going to be that change. That energy change is the enthalpy.
Is it possible to have a closed system with a constant pressure but variable volume? Because once the volume changes, will the pressure change as well?
Not if it's generating heat, that's going to push that volume out at constant pressure. So the heat's going into making the gas expand.
Oh, okay. That makes sense.
And so then this is a more sensitive way to do calorimetry. This is looking more for phase changes. The bomb calorimetry is looking at heats of reaction. It's not just combustion. You could actually, they have an attachment in there that you can release, say, a solid into a liquid and look at the heat of dissolution. So when the solids dissolve in the liquids, you could measure the heat change in that. So the bomb calorimetry is useful for a lot of different solution and reaction enthalpy changes and entropy changes, not enthalpy and energy changes. But this one is comparing a sample and reference to get very sensitive melting points, very sensitive polymer transformations. So phase changes, the differential scanning calorimeter is useful for. And so we have the opportunity to run experiments on the DSC. The problem is that they take quite a while to run. So just measuring, say, a melting point might take 30 to 40 minutes for a single run. And, if everybody's going to do that, we just have one instrument. And so in a 4-hour lab period, we could get through 6 people, maybe. And so we might open that up to where if somebody wants to focus on learning differential scanning calorimetry, we might be able to swap some things around and come in at different days, or maybe start that earlier during the bomb calorimetry part, so we could stretch it into 3 weeks. And so just, if that's something you really want to learn, DSC, when is it used? Well, DSC is used in material science. That's where I've run across it the most. Working with polymers, learning how to look at glass transition temperatures or other kinds of phase transitions in polymers, crystallization of polymers. And so if somebody is interested in that field of chemistry, then visit with me and maybe we can do even some swapping. Maybe you could do this instead of bomb calorimetry. I'll work with you because we have that flexibility. So there's also a difference in this work term between enthalpy and internal energy. And essentially it's related to the net change in the number of moles of gas. And so this is calculating the PV work term, which is the difference between enthalpy and internal energy. If the number of moles of gas hasn't changed in the reaction, then this would be 0. But in this case, for like water, you have hydrogen and oxygen combining to make liquid water. And so we've lost 3 moles of gas. And so that -3 moles change would give us 7.4 kilojoules of difference between the enthalpy and the internal energy. So let's review the equations that we've covered so far. So this is the main slide for this first long set of notes. We've talked about irreversible expansion, which is just expansion against a constant pressure. And we just take the volume final minus the volume initial. If it's compression, then volume final is smaller than volume initial. And so that delta V will be negative, which will cancel the negative sign and will show positive work. So mentally think about what positive work means. That means work's been done on the system. So the system has gained energy and now has a higher capacity to do work. So when we have a cycle problem or we have an engine, there'll be an expansion leg where the system's doing work on the surroundings, and there'll be a compression leg where the surroundings are doing work on the system to reset it. So it's using, you put in heat, you do work, and then you take heat out, and you work on the system to reset it. And so then this cycle turns heat into work through expansion and compression. If we had isothermal reversible expansion, then it's this logarithmic dependence upon the change in volume. And so if you see these words, isothermal, reversible, then this is the equation you would use for work. And then if you have constant volume, both of these are going to be 0 up here. Work would be 0, and the change in internal energy would just be using the change in temperature. And so if you have the change in temperature, and you have the heat capacity for the system, the number of moles, you can calculate the change in internal energy. In terms of enthalpy, if we're at a constant pressure, then the change in heat will give you the enthalpy. You could find the change in enthalpy using the change in temperature at constant pressure. And then this right here, this equation is probably the most important on the page, because you can convert from CV to CP and back, because there's just 1 R difference between the two. So anything on this page that I can clarify, we will use all these equations, so you'll actually learn them by doing. I just wanted to introduce them in this first lecture. Let's cover now the second and third laws of thermodynamics, which deal with entropy.